by the new chromosome. It's sort of the ultimate test in proving that this is the information of biology and dictates what a cell can do and maybe even should do. This was a precursor to being able to now design life, build synthetic molecules by looking at individual genes. We now have some gene families where we have 30, 40, 50,000 members, natural variants that occur in the population. And we have major problems we're trying to overcome by looking for solutions, changes in modern society. The first uses we're trying to put these to is trying to come up with alternate ways of making fuel. Instead of taking carbon out of the ground, looking at this diversity of biology, we have thousands, perhaps tens of thousands of organisms that can take the energy from sunlight, carbon dioxide from the environment, fix the carbon from the carbon dioxide, and also make a potential fuel, natural gas, such as methane. When we look at cells as machines, it makes them very straightforward in the future to design them for very unique utility. So I think all these speak against that one quotation.
It's more than just saying that you can pick up a chromosome and put it in somewhere else. It is pure information. You could put it into a printed book. You could send it over the internet. You could store it on a magnetic disk for 1,000 years, and then in 1,000 years' time, with the technology that they'll have then, it will be possible to reconstruct whatever living organism was here now. So this is something which was utterly undreamed of before the molecular information revolution. What has happened is that genetics has become a branch of information technology. It is pure information, it's digital information, it's precisely the kind of information that can be translated digit for digit, byte for byte, into any other kind of information and then translated back again. This is a major revolution. I suppose it's probably the major revolution in the whole history of our understanding of ourselves. It's something that would have boggled the mind of Darwin, and Darwin would have loved it, I'm absolutely sure.
And for this conference, it's almost as important as advertising online.
I didn't hear that.
Well, to speak to this point, for the last 15 years, we have been digitizing biology. So when we decode a genome, including sequencing the human genome, that's going from what we consider the analog world of biology into the digital world of the computer. Now, for the first time, we can go in the other direction. So with synthetic genomics and synthetic biology, we are starting purely with that digital world. So we take the sequence out of the computer, and we chemically, from 4 raw chemicals that come in bottles, we can reconstruct a chromosome in the laboratory based on either design, copying what was in the digital world, or coming up with new digital versions. And in fact, somewhat jokingly, we can argue that this is the only nanotechnology that actually works. Biology is the ultimate nanotechnology, and it can now be digitally designed and reconstructed.
There are people who are very uneasy about this kind of science. They sometimes call it scientism. And there's a certain suspicion of arrogance. The phrase playing God has been brought up. I don't think I have a problem with that, but I think it's something we ought to take seriously. What I do have a problem with is the possible unforeseen practical consequences of some of the sorts of things not just you are doing, but many other people are doing. I suspect that the phrase playing God is actually a kind of, it's a bit like the boy who cried wolf, because accusing a scientist of playing God is obviously stupid, But what is not obviously stupid is accusing a scientist of endangering the future of the planet by doing something that could be irreversible. And what I mean by the boy who cried wolf is that we may become so used to fending off idiotic accusations of playing God, and thereby humanity might overlook the real dangers. Do you think that's a possible danger?
I think it's a real-life danger that we're facing now. I've argued that we are 100% now dependent on science for survival of our species. In part, science of today has to overcome the scientific breakthroughs of previous years. Because we've advanced internal combustion engines, because we're so good at burning carbon that we take out of the ground, we did it blindly without any consequences of that it might totally affect the future of the planet. Now the numbers, and I've had to change my slides 3 times last year, of the amount of carbon that's going into the atmosphere and staying there. That number is now 4.2 billion tons of carbon. It's accelerating faster than anybody projected. My slide at the start of 2007 was 3.5 billion tons of carbon. It's expected, perhaps, with increasing industrialization of China and India, within 20 to 40 years, that number could be on the order of 20 billion tons of CO2. There are several environmental scientists that have argued there's almost nothing we can do to reverse that now. So we may be fixed in our destiny regardless of whether we have new approaches. I don't like that scenario. I think we have to try and do something. I hope those people are wrong with their projections. If we can do 2 things, number one, replace using the carbon we're taking out of the ground by using renewable sources, and the best renewable source we have is energy from the sun. Over 100 million terawatts a day hit the Earth. We have cells that capture carbon back from the environment, and it turns out chemically and biologically in the lab we can make anything in the lab that comes out of the ground in terms of carbon. We can make octane, we can make diesel fuel, we can make jet fuel, we can make butanol, ethanol. Humanity's been making that forever through simple fermentation. These are ideas that are slow to catch on. Very much in the notion that you're talking about, people are much more concerned that there might be new consequences of engineering biology than this potential disastrous route we're on, totally changing our atmosphere, maybe making it impossible ultimately for our species to survive. I think that's a far more dangerous experiment.
Did I understand you to be saying that whereas the energy we get out of the ground, oil and coal, took millions of years of all those terawatts of sunlight hitting leaves in the Carboniferous and being stored, do I understand you to be saying that now, with the biotechnology that you are doing, it should be possible to capture those terawatts of energy on the fly, as it were, and use them in the present rather than stored over millions of years from the past and dug out of the ground?
Exactly. What we're doing with burning oil and coal is we're taking millions of years of compressed biology, we're burning that over the course of years and putting it in the atmosphere. We can do just the opposite. We can even capture back some of that CO2. It only takes about 1% of the sunlight that hits the Earth daily to replace all the fuel we use, all the energy we use for transportation. These are not huge leaps. There's just been no motivation for it because oil was cheap. We've gone through this cycle, I think, 2 times now where people rapidly pursued alternative energy sources, then the cost of oil dropped. In fact, that's my biggest concern now. The price of oil is in the hands of very few people, and if there's truly alternatives that come on the market, the cost of oil could be artificially dropped to really low prices, killing off these new industries.